I gotta take that lesson. Proud of you. I'm proud of you.
So I've been having a little bit of trouble with the camera. So if the camera stops working, then if you're at home, I'll try and record next period and send it or something, but hopefully it won't stop working. I don't know what's wrong with it. So anyway, so as you guys know, we were supposed to take the test the Thursday before break, but we didn't have school. So the test was actually postponed until this Friday for everyone except Sophia. She took it already.
Yeah, love that.
So she's all done. But anyway, yeah, so the test will be this Friday. So what we're doing the rest of the week is there's a couple of topics that have to do with limits that I skipped over or didn't really cover just in the interest of time. But since we have a little time here, so we'll do those topics. And then, so that'll be on Monday, Tuesday, Thursday. Wednesday will just be a free day. And then Friday will be the test. The topics that we cover this week aren't going to be included on the test, but they're just topics that I want you to have exposure to at some point. So what I'm talking about, or what your teacher is talking about when you take calculus in college or whatever. Okay?
Okay.
All right, so today we're going to talk about special trig limits. So trig functions in general follow similar rules as rational functions or any polynomial or something like that. Like if I have a trig limit, like suppose it was like the limit as x goes to 4 of sine pi over x, something like that. I mean, if you could just substitute 4 in and it makes sense and it gives you an answer, then that's the answer. That's all there is to it. This just ends up being sine pi over 4. Pi over 4 is 45 degrees. So this ends up being radical 2 over 2. Okay? So generally, what I'm saying is trig functions follow the same rules for limits as other types of functions. Now there's a couple of special situations that are a bit confusing at first, but if you look at it the right way, it sort of makes sense. So one example is, what if you wanted to find the limit as x goes to 0 of sine x over x? Now, we definitely can't just substitute this in, right? Because I would get 0 in the denominator. But another really important notable thing is I also get 0 in the numerator. And normally, what happens if you have 0 over 0 when you substitute the number in? Like if it's a rational function, what happens there? It's good that we're reviewing this, right? So normally, it's definitely not 1. Yeah. No. Normally, for rational functions, if you get 0 over 0 by substituting an x value in.
Oh, that's what.
Yeah, right. Good. What did you say? So yeah, it's a hole in the function. By substituting in a particular x value, then the function has a hole at that x value. So for example, if you have something like, remember like f of x equals x squared minus 1 over x minus 1, right? This has a hole at x equals 1. because if you substitute in x equals 1, you get 0 on top and you get 0 on the bottom. And to determine the actual like y coordinate of that hole, you could just cancel the common factor, right? You could think of this as x minus 1, x plus 1 on the top, x minus 1 on the bottom. These would just cancel, and you get x plus 1, right? That means that this function, this original function f of x, looks exactly like x plus 1, but the original function has a hole in it at 1. To find the y coordinate of that hole, you would find the limit as x goes to 1 of f of x, which is just 2. It's what you would get by substituting 1 into this expression here. Does that make sense? Does that ring a bell for everybody that we talked about that? Okay, so in this function, I get 0 over 0. So my intuition tells me that there should be a hole in the function. But I don't know what to do algebraically to figure out like what the y coordinate of that hole is, which is actually the limit that I'm looking for. Like, right? If I'm trying to find the limit as x goes to 0, and I know there's a hole in it, then my goal should be to figure out the y coordinate of that hole, because that's the y value that the graph is approaching as you go towards 0, right? So my limitation here is it's not factorable. It's not something else we've done algebraically, which includes, we talked about what if it's a complex fraction. We talked about what if there's radicals involved and you do this rationalization thing. We talked about just factoring in general. So we talked about all these different ways, but we didn't talk about something like this, okay? So that's what I wanted to talk about today, is how to calculate this limit as x goes to 0 of sine x over x. And it turns out that algebraically, you really can't do very much. But what you can do is you can look at the graph of that function. And we know that looking at graphs of functions, we can sometimes figure out what the limit is by looking at the graph, right? So that's what we can do here. We can find limit as x goes to 0 of sine x over x by graphing the function. So I'm going to graph it on Desmos, but you could graph it on any graphing calculator. So I have Desmos here. Open already. So on Desmos, all you have to do is you just have to type in the function over here. So I'm just going to type in sine x over x, or sine x over x, like that. Now, if my calculator was in degrees, this would be way boringer. It just looks like a vertical line, a horizontal line rather. And no matter how far I zoom in, like it would still just look like a horizontal line, although you can see it's not the x-axis itself, it's like a little bit above that. And I can sort of figure out what it is by getting closer and closer, but not that interesting. It just looks like a horizontal line. But changing the calculator to radians makes it way more interesting. Now it's not on here, but that's because I'm zoomed way in. If I zoom back out, the default zoom, you can kind of see what's happening. It looks like it's going towards 1, right? Now, the actual graph is undefined at 0, for sure. Like if I click on that point, you can see it's undefined at 0, which we know that already. You can't plug 0 in because it's 0 over 0. So it's definitely undefined. But if I go to either side of it, it's really close to 1. It's so close that it says it equals 1. If I get further away, you can see it gets further away from 1. But on both sides, it's definitely approaching 1 from both sides. So what this graph looks like, just based on a graphing calculator, it kind of looks like cosine function in a way, where the further out you go from the y-axis, the amplitude gets smaller and smaller. That's what this graph looks like. It kind of goes like this. There's a hole there, and then it goes like this. Like it has the x-axis is an asymptote, but it keeps crossing that asymptote and getting closer and closer from each direction like that. This way, that's the same thing. So it just goes like that. But the point is, the limit is 1. Okay? The limit as x goes to 0 of sine x over x equals 1, because that's the y coordinate of that hole. Okay? Now, there's other ways that you can get this that involve way more sophisticated like calculus work, which is the reason why I skipped this topic to begin with. Okay, so I don't want you to think that I'm just like randomly skipping things that you're going to need someday, because there's a kind of an easier way to do this if you know a little more calculus, which is what I normally do. I would wait until you know a little more calculus, and then I'll say, remember when we talked about limits and we had this situation? Okay, and then we use this other little method to find the limit just like super simply, okay? But since we have a little time, like I said, we can also do it by just examining the graph, and that's what it ends up looking like, okay? So that's one of the special limits I wanted to talk about. There's 4 of them that we're going to talk about today, okay? The second one is, what if you have the limit as x goes to 0 of x over sine x? Now, obviously, it's the same situation. I get 0 over 0, but the graph looks much different. And again, I could find it by using Desmos or any graphing calculator, or I could try and just reason through, like, if you just think about, like, what would the reciprocal of this graph look like? 1 over this graph. Well, I mean, definitely any point where this graph is 0, its reciprocal is going to be undefined, right? So what's going to happen is you're going to end up with a graph where it has these vertical asymptotes that are getting closer and closer and closer together. So that's one thing that's sort of weird about it. You're going to have these asymptotes that get closer, 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 closer together, right? And going this way, same thing, these vertical asymptotes that are going to get closer and closer and closer together. And then what happens in between these asymptotes, it's super weird too. But what it ends up looking like, I'll just do it. I mean, definitely the reciprocal of a positive is a positive. So this stuff's going to be up here somewhere. And the reciprocal of a negative is going to be negative. So this stuff's going to be down here. So it's going to be like up here and then down here, and then up here and then down here, and then up here. So it looks almost like a secant curve, or one of those ones where you have like a parabola here and a parabola there, a parabola here, and a parabola. It looks kind of like that, but weirder. So if I go back to Desmos and I graph x over sine x, not that interesting from this view, but if I zoom out, you can see it's kind of like what I described. It just kind of looks like that situation. It's sort of weird, but reasonable. If you think about what the graph of sine x over x looks like, it makes sense that these are getting like bigger and bigger y values, because the x values or the y values in the original graph are smaller. So it makes sense that their reciprocals are bigger, right? Kind of. So it ends up going like this. There's a hole right here, goes like that. And then there's going to be like these 2 things that go like this. And then further away, like 2 things that go like this. And then further away, like 2 things that go like this. And further away, and so on. And it looks like that. But all we care about is what's happening near 0, and the limit's 1. Because up here, the limit's 1. The reciprocal of 1 is 1. So it makes sense that the reciprocal of this graph is going to look something like that, right? It's still going to have that same hole. So this limit is also 1. Okay. Any questions so far? I hope this isn't too confusing. Basically, we're just taking a situation where we know there's a hole in the graph, We just can't figure out what the y-coordinate is, so we're just looking at the graph to find out what the y-coordinate is. That's the whole point. So you don't have to memorize what these graphs look like or anything like that. We're just like going through the process of finding limits. That's it. So there's two more, like I said. The next one, different. The next one is, what if you have the limit x goes to 0 of cosine x minus 1 over x. So I know if I take the cosine of 0, I get 1, right? So if I plug in 0 here, I get 1 minus 1 on top, definitely 0, and I get 0 on the bottom. Same situation, 0 over 0. I know there's a hole in the graph, and there's nothing algebraically I can do to this. Like I can't do factoring, I can't, like, there's no complex fraction to get rid of, there's no rationalization that would make sense here. So again, I'm just going to look at the graph of the function. Okay? So if I graph this function, cosine x minus 1 over x. Let me go back to just a normal default zoom. So I can delete this. So if I go cosine x, whoops, I think I need parentheses. Cosine x minus 1 divided by x. All right, so this doesn't look very interesting, but one thing that's definitely true, like if you look at just to the right of the y-axis, it's always negative or 0, which kind of makes sense because if you take cosine values always fall between 1 and negative 1, right? So if you subtract 1 from a cosine value, it's going to be something that's less than 0 for sure, less than or equal to 0, right? Because you're taking something that's less than or equal to 1 and you're subtracting 1. So you're going to get something less than or equal to 0. So it kind of makes sense that this part of the graph is completely below the x-axis, and vice versa, this part of the graph is completely above the x-axis, right? Because in that case, the denominator is negative, so you have a negative over a negative, right? So it makes sense that stuff's positive. Okay, so what this ends up looking like, if I graph it a little bit more like just hand drawing, it looks like this. There's a hole right there, and then it kind of looks like a sine wave or a cosine wave that just touches the axis and just keeps getting closer to it like that. So it goes away from the axis and then back to it, and then away less far and back to it, and away less far, back to it. And then on this side, it kind of just does the same thing, but in reverse, and just goes like that. Okay, that's what this graph looks like. It's just hard to tell. It's all digitized like that, but that's what it looks like. Does that make sense? Mm-hmm. So what's the answer? Yeah, 0. That's where that hole occurs, is at 0, 0. This limit is 0. Everybody with me so far? Okay, there's one more. The last one is similar to this one. Is the limit as x goes to 0 of 1 minus cosine x over x. And if you just look at like what's the difference between this function and this function, they're just negatives of each other, right? If you switch the direction of a subtraction, that's just like making the whole function negative. This is really like 1 minus cosine x over x is really the same thing as the negative of cosine x minus 1 over x. Well, what happens graphically if you make a function negative? Like, how would this function look different than this function? It's okay. What do you think it is?
Oh, it's so like,
That's it. It reflects it over the x-axis, right? We talked about this earlier in the year. If you take a function and you make it negative, it reflects it over, it flips it upside down. It reflects it over the x-axis, right? So this graph is going to look exactly the same as this green graph, except where it's just going to be in the opposite quadrants. Like it's going to be a hole here, but then it's going to go up first, do something like that, and then down over here. That. It's just the flip of that function. So this limit's still going to be 0. Right? Like if I go to Desmos again and graph this, I'll even graph it on the same set of axes. Like if I graph 1 minus cosine x divided by x, you can see it's just totally the reflection of that original graph. It looks exactly the same. Okay? So there's 4 special limits you need to be aware of here. All right?
so are the inversions not really notable? Like the inversions of those?
Inverses. You mean reciprocal?
Yeah, that's what I mean.
I don't know. Let's see. Let's see what happens. I mean, I'm thinking it's not going to be possible because if the limit's 0, the reciprocal at that point is going to be like something totally weird. I think there might be an asymptote or something. Let's see what happens. I don't know. I've never considered that. That's a great question. So let me delete these. Let's take x over cosine x minus 1. Yeah, see, like I said, it makes sense that the limit doesn't exist because if the limit of the original function is 0, then the limit of the reciprocal would have to be the reciprocal of 0, which is non-existent. You know what I mean?
Yeah.
So kind of, I mean, yeah, this is an interesting looking graph, but this isn't one of the ones that we're talking about because it doesn't have a limit at that point. You know what I mean? Whereas the other ones do. So really great question. All right, so the 4 special limits you need to be aware of, let's just review here. They are the limit as x goes to 0 of sine x over x equals 1. The limit as x goes to 0 of x over sine x equals 1. The limit as x goes to 0 of cosine x minus 1 over x equals 0. And the limit as x goes to 0 of 1 minus cosine x over x equals 0. So those are the 4 special limits that are important. Tomorrow, we're going to talk about special trig limits that are like variations of these. Sometimes these limits are changed in a certain way so that you get a little bit different answer, but it's using the normal like laws of limits that enable you to get those other answers. And we'll just talk about like how that might look and stuff like that. Any questions? Okay, so there's no homework tonight. For tomorrow, there is an assignment. It's on IXL, but you're not quite able to do it yet, so I wouldn't try it yet until we do tomorrow's work. And then for Thursday, we're going to talk about another topic, and there's no homework for that. So the only homework for this week is that one IXL assignment, which will be possible to be done tomorrow. Any questions? Yes. Yeah, sure. All right, I'm going to stop recording.